Have you ever wondered how energy, heat, and work interact and transform? That's what the science of thermodynamics studies. Imagine the universe as a grand stage, and everything that happens within it is part of a complex play. In the realm of thermodynamics, the part of the universe we're interested in is called a system. This could be anything from a boiling kettle to the engine of a car. Everything outside this system is deemed the surroundings. Now, every system is defined by its state, which is characterized by properties like temperature, pressure, and volume. Think of it as the system's unique ID, a snapshot of its current condition. These properties hold the keys to understanding the behavior of the system. When these properties change, we're witnessing a process, a transformation in the system's state, and it's these transformations that are at the heart of thermodynamics. In the world of thermodynamics, changes in these states are what we call processes. Thermodynamics is governed by 4 fundamental laws. Let's start with the zeroth law of thermodynamics. It may have an odd name, but its idea is simple. If 2 systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. Essentially, this law allows us to establish the concept of temperature. Next, we have the first law of thermodynamics, also known as the law of energy conservation. It states that energy cannot be created or destroyed, only transferred or converted from one form to another. Think of it like a bank account. You can't just magically create money. You either have to earn it, save it, or transfer it from somewhere else. Similarly, energy in a system can be transferred or converted, but the total amount remains the same. Moving on, we arrive at the second law of thermodynamics. This one is a bit tricky. It states that the total entropy of an isolated system always increases over time. Entropy, in simple terms, is a measure of disorder or randomness in a system. So the second law tells us that things naturally move from order to disorder. If you've ever tried to keep your room clean, you've experienced this law firsthand. Finally, we have the third law of thermodynamics. This law tells us that as the temperature of a system approaches absolute zero, the entropy of the system approaches a minimum. In other words, as things get colder and colder, they become more and more ordered. This law is why it's impossible to reach absolute zero temperature. There's always a tiny bit of heat, and therefore a little bit of disorder, left. These laws govern the way energy moves and changes, and they set the stage for understanding heat and work. So, how do heat, work, and energy play into this? Let's dive into the heart of thermodynamics. First, heat, symbolized as Q, is the energy transfer due to a temperature difference. It's like the warmth you feel from a hot cup of coffee. Work, represented by W, is the energy transfer associated with a force acting through a distance. Think of it as pushing a heavy box across the room. Then we have internal energy, denoted as U. This is the total energy contained within a system, like a pot of boiling water. Now, this internal energy can change in 2 ways. It can either be due to heat transfer, like when you heat up that pot of water on a stove, or due to work done on or by the system, like when you shake a bottle of soda and it bursts open. Understanding these elements brings us closer to grasping how energy systems behave. Let's explore a bit more about enthalpy, entropy, and thermodynamic processes. Enthalpy, symbolized as H, is the sum of a system's internal energy plus the product of its pressure and volume. It's particularly useful in processes that occur at constant pressure. On the other hand, entropy, represented as S, is a measure of a system's disorder or randomness. According to the second law of thermodynamics, entropy in an isolated system always tends to increase over time. Now let's touch on thermodynamic cycles. Consider the Carnot cycle, a theoretical cycle that provides an upper limit on the efficiency that any heat engine can achieve. On the flip side, we have the Rankine cycle, commonly used in power plants, which involves a steam generator, turbine, condenser, and pump to convert heat into work. These cycles and the concepts of enthalpy and entropy are fundamental to understanding the energy transformations that drive our world, and that's a quick dive into the fascinating world of thermodynamics. So, what have we covered today? Quite a bit, wouldn't you agree? Let's take a moment to consolidate our understanding and recap the key points we've discussed. We embarked on our journey with the fundamental concept of system and surroundings. A system, remember, is the specific part of the universe under consideration. It's the focus of our curiosity, the subject of our study. Everything outside of this system, the rest of the universe in essence, is what we refer to as the surroundings. These 2 entities, the system and its surroundings, interact with each other in various ways, driving the phenomena we see and experience every day. We then moved on to the notion of states and properties. The state of a system is defined by its properties, such as temperature, pressure, and volume, which are characteristics that define the state of a system. A change in any of these properties results in a change in the state of the system, something we refer to as a process. Now, processes can take different forms. They can be adiabatic, where there's no heat transfer, isothermal, maintaining a constant temperature, isobaric, maintaining a constant pressure, or isochoric, maintaining a constant volume. Each of these processes represents a unique way in which a system can change and evolve. Next, we delved into the laws of thermodynamics, the fundamental principles that govern the behavior of systems. Starting with the 0th law of thermodynamics, we established the concept of temperature. This law states that if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. The first law of thermodynamics, also known as the law of energy conservation, tells us that energy cannot be created or destroyed, only transferred or converted from one form to another. This is a fundamental principle that underpins much of our understanding of the physical world. The second law of thermodynamics introduces us to the concept of entropy, a measure of the disorder or randomness of a system. According to this law, the total entropy of an isolated system always increases over time, and any reversible process must increase the total entropy of a system and its surroundings. Finally, the third law of thermodynamics states that as the temperature of a system approaches absolute zero, the entropy of the system approaches a minimum. This law gives us insight into the behavior of systems at extremely low temperatures. After the laws of thermodynamics, we explored the concepts of heat, work, and internal energy. Heat is the energy transfer due to a temperature difference, and work is the energy transfer associated with a force acting through a distance. The total energy contained within a system, including the energy due to its temperature, chemical composition, and other factors, is its internal energy. This internal energy can change due to heat transfer or work done on or by the system. We then discussed enthalpy, a concept that is particularly useful in constant pressure processes. Enthalpy is defined as the sum of the internal energy of a system and the product of its pressure and volume. Finally, we touched upon the topic of thermodynamic processes, using different thermodynamic cycles, such as the Carnot cycle or Rankine cycle, to analyze and describe the performance of engines and refrigerators. In essence, thermodynamics provides a framework for understanding and describing the behavior of systems, particularly in terms of energy transfer and transformation. One that illuminates the underlying principles that govern much of the world around us. So, that's it for today's journey into the world of thermodynamics. We've covered a lot, and hopefully you now have a better understanding of the various concepts and principles that underpin this fascinating branch of physics. Next time you see a steam engine or a refrigerator, you'll have a better understanding of the physics at play. The heat, the work, the transformation of energy, it's all part of a grand dance of particles and forces guided by the laws of thermodynamics. Until then, keep questioning and exploring.